In this lecture, we are going to answer the question, how does a model learn? Let's start with linear regression. In its most basic form, linear regression just means line of best fit. As you may recall from your high school math studies, a line has the equation y equals mx plus b. Here, x is the input variable, m is the slope, and b is the y-intercept. When we put these together, we get the equation for a line. And our job, of course, is to find the line that best fits our input data. So you can imagine that our input data is a bunch of data points that approximately create the shape of a line. This plot is called a scatter plot. So for each point x and y in our data set, we're going to draw a dot on this chart. Our goal is to find the line that best passes through all these data points. In practice, this means finding the slope and y-intercept. One method you may have used in high school is to take a ruler and to try and draw the best line on paper using visual inspection. Of course, since this is data science, we no longer use such methods. We have to be more systematic. The line that you draw might not be the same as the line that I draw. And furthermore, if we are in multiple dimensions, this won't be a line at all. So it's clear that we need something better and more quantitative. The idea is we're going to define an error function. For each data point, which is a pair made up of the input xi and the target yi, we are going to calculate a prediction y hat I equals to mxi plus b. Then we are going to take the square difference between yi and y hat I. We're going to do this for each of our data points for I equals 1 up to n. Once we've done this, we can add them all up and divide by n. This is called the mean squared error. It's the average squared deviation between our predictions and our targets. Basically, this is going to tell us how accurate our model is. If our predictions are equal to the targets, then this error will be 0 because yi would be equal to y hat I. Then, the more wrong we are, the larger this error becomes. So that's generally how an error function should work. As a side note, since some students get confused by this at first, we have multiple names for this error, and we usually use them interchangeably. Sometimes we call it a loss, sometimes we call it an objective, or sometimes we call it a cost. However, these all mean the same thing. I like the term cost because it makes intuitive sense for business people. As any good businessman would do, your job is to minimize your cost. And in fact, this statement alone tells us how to find the weights W. So how do we minimize this cost, or in other words, make it as small as possible? Well, it's time to turn to our old friend calculus. If you recall, we can find the minimum or a maximum of a function by finding where its derivative is equal to 0. If you're not convinced by this, try to draw a curve which has a minimum or a maximum, and draw the slope at the minimum or maximum point. If you drew your line correctly, it should be a horizontal line, meaning that the slope at this point is 0. And remember, the slope at each point is just the derivative, so that's why we want to find the derivative, set it to 0, and then solve for the parameter in question. Now, usually, we have more than one parameter. Even in one-dimensional linear regression, this is the case because we have both the slope and the y-intercept. So what happens when we have a function of more than one variable? In this case, the derivative is actually called the gradient. If you recall from your calculus studies, the gradient is just a vector or tensor of partial derivatives. For each of the variables, we're taking the gradient with respect to. So for example, if you take the square function in one dimension, that's called a parabola. But if you have two input dimensions, it's called a paraboloid. Beyond that, we can't picture it, but the basic idea is still the same. Find the gradient, set it to 0, solve for the parameters. By the way, the term parameter is just another name for the weights. So that's the W and B we've been referring to throughout this section. Luckily, in this course, we won't be calculating any derivatives manually, since I have many other courses which do that a lot. And by a lot, I really mean a lot. So in this course, we're kind of excused from doing that because PyTorch already does that for us using a process called automatic differentiation. Luckily, you don't have to know how that works either because as its name suggests, it's automatic. So the only thing you really do have to know is that A, PyTorch is going to automatically find the gradient of all your weights, and B, PyTorch uses these gradients to train your model. At this point, you might be wondering, if all I have to do is find the gradient and set it to 0, then why in our previous code did it involve an iterative training process? Recall that we had to specify the number of epochs to train for, and this resulted in a plot of loss per iteration, which we could check to confirm that the training algorithm converged nicely. Well, in actuality, it's not possible to actually solve for the equation that you get when you set the gradient to 0 most of the time. The one exception to this, in this course at least, is linear regression, where we can solve it. We call the solution an analytical solution or a closed-form solution. Basically, this means that we can express the optimal value of W and B using an equation. For logistic regression and the rest of the models we'll be discussing, it's not possible to do this. Therefore, we need another approach. That approach is called gradient descent. Now, there's a lot more to gradient descent than what's in this lecture, and you can check out the in-depth section of this course for that if you're interested. For now, let's just talk about the basics. Essentially, what we do is we start at a randomly initialized point for both W and B. Since this is random, these probably don't lead to a small cost. So then we find the gradient of our loss with respect to W and B. We then take small steps in this direction to update W and B on each iteration. Remember, these iterations are called epochs. Mathematically, you can prove that this leads to a decrease in cost, although we won't discuss that in this lecture. You can imagine that this is exactly what goes on inside the optimizer.step function. This is really all that's happening. For epoch and range epochs, and then set W equal to W minus eta times the gradient of J with respect to W, and set B to B minus eta times the gradient of J with respect to B. So again, all we're doing is taking small steps in the direction of the gradient with respect to W and B. Now, one obvious question that arises from this is, how small should these small steps actually be? Well, the step size is specified by this Greek letter eta, which we call the learning rate. This specifies how fast or slow we want to train our model. It's important to set this value right, because if you don't, then your model won't get good results, even if your model is actually a good model. Unfortunately, there's no direct method of choosing a good learning rate. Generally speaking, the learning rate is something we call a hyperparameter. This is to differentiate it from W and B, which are just regular old parameters. It's called a hyperparameter because it's still a parameter, but it's not a parameter of the model itself. It's sort of like a meta parameter. And in fact, no hyperparameters are really chosen directly. It's more of a process of trial and error, along with intuition that you gain from practicing a lot and seeing a lot of different examples. As mentioned before, one way to know if your learning rate is too high or too low is to check the loss per iteration after training. This is somewhat unfortunate because training can take a long time, and you only know the result once it's done. If you use a bad learning rate and got bad results, well, you still had to wait for them. I really like this visualization because it encapsulates how to choose the learning rate quite well. If your learning rate is too high, then your loss will just shoot off to infinity. Intuitively, this is because you're overshooting the minimum and just ending up on the other side of the canyon. That means your steps are too large and you need to make them smaller. Sometimes your learning rate might be a bit too high, so you'll see some convergence, but it'll converge to a suboptimal value. If your learning rate is too low, then you'll see a really shallow curve. This is also not good because, as I mentioned, training takes time. So if your learning rate is too low, you'll have to wait longer. But not only that, sometimes you can just get stuck at a suboptimal point. That's also not good. A good learning rate is in between these two extremes, and so what you'll probably end up doing is finding the limits of your particular data set, what's too high, what's too low, and then trying different numbers in between until you find something good. Normally, we try numbers that are powers of 10, for example, 0.1, 0.01, 0.001, and so forth.